Hey there, 2200, welcome back. Today we're going to do Lab 9, which is AC circuits, impedance and resonance. Unlike the last time though, if you did the last time with me, we're not going to do it together. So this video isn't going to be an hour long, it's going to be more like 5 minutes or so. The purpose of this video is to show you exactly how we go about collecting the data, and you'll just be supplied with all the measurements, and then you can do your analysis on your own. So first thing that we're going to do is build this circuit here, and what we want to do is determine the impedance of this circuit element here. Now we're going to do that for 3 different circuit elements: a resistor, a capacitor, and an inductor. In part A, we'll be determining the impedance of each of those elements separately. So the way we want to do that is simply measure the voltage across our component of interest, we'll call it Z, then divided by the current. Problem is we can't determine that current just by this voltage here. What we'll do is we'll measure the voltage across this standard resistor. And once we measure the resistance across this standard resistor, we'll of course divide it by the resistance. This particular standard resistor is going to be 10, it's rated at 10 ohms, it measures at 10.2. So if we could determine the current across this resistor, we therefore know the current across this component as well. From Kirchhoff's rules, if I know the current here, I know the current there. Current isn't building up anywhere around the circuit or leaking, so once I find the current there, I'll know what it is across Z. Then I could divide voltage by that current and determine the impedance. And this is done, of course, because unlike a resistor, certain components like inductors and capacitors have frequency dependency. So what we'll do is we'll vary the frequency of our source, get about 20 data points, and determine how that affects the impedance. By the way, this is what is called a floating circuit, meaning it's not grounded. So according to this circuit here, I could simply place my oscilloscope across Z, measure the voltage, and then across R here and measure the voltage. But our function generator is grounded, and our oscilloscope that's going to be attached across Z here is grounded. So both of those instruments need to be grounded at the same spot. So as it stands from this picture here, if I had the oscilloscope in this position and grounded it here and grounded the function generator here as well, I could easily determine the voltage across that element. But I couldn't put it here because it would be grounded in a different spot. So to circumvent that problem, we set up this circuit here using a double pole, double throw switch. It looks complicated, but it's already set up. And right here on the bread box, I have the 3 different components of interest. I have a resistor, an inductor, and a capacitor, and right here is my standard resistor. Actually, I see that there's a diode here, but that's for a previous lab. We're not gonna touch that diode. So when I have this switch in the upright position, channel 1 is measuring the voltage across my experimental resistor. So to find out the impedance of this resistor, I'd measure that voltage. Then I'd put the switch in its lower position, and that measures the voltage across my standard resistor. So I would record that for a certain frequency, then change the frequency with my function generator here. For instance, right now it's at 5.99 kilo ohms. Let's say I wanted to put it at 10. So now it's about 10, and I do another measurement. Remember, the switch in the top position would be my voltage across Z, so I could determine the peak-to-peak voltage on channel 1, which is 7.84. Then to find out the voltage across my standard resistor, I put this in the down position. Let me scale this a bit. My peak-to-peak is, it's fluctuating. But it's around it's around 1 volt. If I was doing the experiment right now, I would get rid of that noise, but I'm just going through a run through of how the data was collected. So for part 1, where you're measuring the impedances across individual components, you would vary this function generator to 20 different frequencies for this element, then separately for this element, then separately for this element, and measure the voltages both across the element of interest and across your standard resistor. So for part 2, what we want to do is actually measure an inductor and capacitor in series. So I'm going to connect these two and put my oscilloscope across these two elements. And for this one, for instance, it suggested that you start off with like 50 hertz. So for 50 hertz, you would put this on its 10 hertz scale and lower it. I lied. It's 10 hertz scale. Okay, pretend I didn't say that. I put it back on the 100, and I could raise this to 50. Some of the data you're provided with those frequencies aren't going to be even nice round numbers, and this is the reason why. Let's say my target frequency is 50. I'm not going to spend like 5 minutes trying to get it right at 50. I'll just leave it right at 52. So I would, as a measured data point at say 52 hertz, I would be getting across my Z a voltage that looks like that. Now, I have some other test equipment in the background that's creating noise. I could fix that, but again, right now I'm just demonstrating how we took the data. So let's say that was a clear reading, and I read the peak-to-peak voltage. That's across my inductor and capacitor. So I have a voltage across there. Now I want to know the current. So to find the current, again, I want to measure the voltage across this standard resistor. So I flip the switch in its bottom position, adjust this scale, and read the peak-to-peak voltage on that curve there. So that would be your collection of your first data point. Or I should say, the measurements needed to calculate what your first data point would be on your graph. Then we'd move up the generator to say 100. let's say I wanted to just quit there. So I would record 109, 109 hertz and read the frequency. Right now it's in its lower position, so that's the voltage across the standard resistor. I think I said read the frequency. I meant read the voltage. Double pole, double throw switch goes in the up position. That means now the oscilloscope is connected across these two elements, and I would read the voltage across those two guys. Then I would repeat 18 more times. Or I'm sorry, I think in the part 2, they just want 12 readings. The first part, you'll find that there are 20 different frequencies for each component. Then when you're dealing just with the capacitor and inductor, they ask for 12 different frequencies. So for part 2, what they first want you to do is find the frequency which gives the maximum amount of current. To do that, what you're going to do is put the switch in the up position, so you're measuring the voltage across these two components, and find the maximum voltage across there. And you would have an idea of what frequency that is because you could calculate it with the formula. So what I did was I went to approximately that frequency with the function generator, and then just messed with it, fine-tuned it while I watched the voltage on the oscilloscope, and tuned it until I saw a peak in the voltage. And at that peak in the voltage, I then recorded the frequency and labeled it as F max. In your lab manual, they talk about 2 frequencies with maximum value. Well, theoretically, they're the same frequency, but they're obtained in 2 different fashions. F max was obtained just like I explained, and F naught is, again, the frequency which produces the max amount of current, but it's determined theoretically from an expression. And that's reported in your table as well. Then the next thing they want you to do is find the frequency that gives you half amount of the maximum current. So you tune this function generator below that maximum frequency and watch your oscilloscope until you see that the voltage is half as much as it was at its maximum value, and record the frequency at which that happened. Then you move your function generator to a higher frequency above that max frequency value, so that you're on the right side of that curved peak, and find again a matching voltage that is half the value of your max voltage. Then they want you to do that as well for not only half the max current, but 0.707 of the max current. And if that sounds totally suspicious, it doesn't make sense, read your lab manual and it will. It has to do with the power delivered to the circuit. But we go ahead and find that 0.707 I max frequency in the same fashion, tuning the frequency generator, and record those values. Again, all of this has been done for you, and it's tabulated. The table that you'll receive with the measurements I did is going to look a little different than the table supplied in your lab manual. In your lab manual, you'll have, for instance, for the first part, this table here, where you're doing your measurements for the resistor. Then you'll have a similar table for your measurements across the capacitor, and likewise one for your inductor. But the table that you'll be supplied with is just going to be one table. So you'll have your resistor data, capacitor data, and inductor data at these given frequencies here. So this is a 2-week lab. It probably, takes hours to do all these measurements, because if you're doing for part 1, 20 frequencies on 3 different components, that's 60 measurements, plus you're measuring the voltage here and here, so that's twice that. That's 120 measurements, and then you move on to part B. But again, all of that's been taken care of. It's tabulated for you, and good luck on the analysis. And of course, see you next time.